Thank you, Lisa. Thanks to you and your staff at the museum here. This really is a wonderful partnership between the Boston Museum of Science and La Fondation Wright in Geneva. That's the Wright Foundation in Geneva, Switzerland, the parent foundation of the Wright Center at Tufts University. This has been an ongoing series on this side of the pond for some 12 years now. We do this series in the odd years in Boston and in the even years in Europe. So if you miss the series in Europe, you can't get to Geneva, just look next fall on the World Wide Web. So welcome to all of you who are just joining us for this talk tonight. Welcome to those of you who have been with us in the previous nights, and again, welcome to those of people who are viewing on the internet. We've been attempting to address the scenario of cosmic evolution, as has been the case throughout this series. We're moving across the archetypical symbol, as I understand it, the arrow of time. We're placing the emphasis on change and on testing. Change because when we look out the window, as Heraclitus did 25 centuries ago, he noted that in probably making the best observation anybody ever made, everything's changing. Whether it's galaxies, stars, planets, or life forms, as we now understand it, a good deal more than perhaps he would have understood. We're trying to place meat on the bones of his skeletal idea. But we as scientists are demanding that these ideas be tested. We're demanding that the ideas be observed and examined through observation, through experiment, and the like. That's the scientific method. That's the central dogma that we have in science. We believe, as scientists, that neither thinking alone nor belief alone will ever make the unknown known. We just demand the test. And by testing and deriving and accumulating more and more empirical evidence, we can hopefully discriminate in an objective way over the course of time between what is sense and what is nonsense, getting rid of the nonsense as quickly as possible and accumulating more and more of the sense as we move progressively, and I think there is a progression there, toward a better and better approximation of reality. So it's an interdisciplinary, integrated story that we tell over the course of Big Bang to humankind. It's an attempt to examine change, physical change, biological change, cultural change. It's a story that ramps up from quarks to quasars, from microbes to minds. In effect, we're trying to build a cosmology here, a cosmology now in which life has an integral role. So we've used this one symbolic form here, this arrow of time, as a one-page summary of where we're going or where we've been. 2 weeks ago, we had a couple of wonderful speakers here, Frank Wilczek and Colin Norman, speaking about the early universe. Were there gaps there? Oh, boy, there are a lot of gaps. A lot of missing links thus far, especially in the early universe. They gave a couple of wonderful talks, but we came away, of course, severely uninventoried. Lots of dark matter, lots of dark energy. We discussed that 2 weeks ago and last week as well. In fact, last week we had another two wonderful speakers, Mike Shire and Dimitar Sazlov, moving us further along the arrow of time and examining the stars and planets. And we didn't agree on a whole lot last week other than the fact that all three of us, I think, did agree that Pluto, it's time to demote Pluto as a planet. So that probably explains this week why I'm starting to get some hate mail from those third graders. And next week we'll push along the arrow of time further, not toward any culminating or pinnacle of cosmic evolution, but we'll reach the here and the now, and we'll have Fred Speer here from Amsterdam and Jill Tarter from Berkeley, the SETI Institute, speculating about how we ourselves have come to be as we are in this grand story of change, in this scenario, and perhaps with the last speaker, Jill Tarter, to make a gesture to the unknown, to speculate where we might be headed as a civilization or as a species. This week we're in the middle part of the arrow of time. You might think that we're crossing the line between physics and biology, but to my mind, it's a longer story at another time perhaps, I don't think there is any line there. I don't think there is any line between physics and biology. I don't think there is any demarcation between inanimate and animate. We are moving toward greater and greater complexity across the arrow of time. In fact, that's going to be a central issue throughout this cosmic evolutionary scenario and in the research domain that extends well beyond these Wright lectures. Because you look out at the window of Heraclitus or whatever, you see nature and you wonder, how is there so much order, form, and structure? And how is it that order and complexity is increasing with time? Despite, if you were to push me as a physicist into the corner, put the bright lights on me, a little like they are now, and say, what is the most cherished law in all of physics, I would have to confess is the second law of thermodynamics, which prima facie would suggest that things ought to be breaking down toward greater simplicity. So can we reconcile the observed constructiveness of cosmic evolution, where complexity over the course of time, at least within islands of ordered structures such as stars, planets, and life forms, seem to be increasing with complexity, with the inherent destructiveness of the second law of thermodynamics. It's a longer story. It's another time. I think we can reconcile those issues. Tonight we bring forth before you then two world-class biologists. They will address the microscopic realm of science and of biology and the bigger macroscopic realm of biology. Our first speaker will address the microscopic domain. Lynn Rostov is an expert from the NASA Ames Astrobiology Institute outside of San Francisco, an expert on microscopic forms of life, algae, protozoa, not only in an Earth-like environment, but in a larger planetary environment, should there be microscopic forms of life elsewhere. She is specializing largely in a wide variety of astrobiological issues, in particular the way in which radiation might harm organisms, a very, very important issue if we as humankind, as human beings, are going to try to move out now toward Mars. How does radiation, how does UV radiation react to or impact on, as NASA would say, using that word as a verb, on organisms? What does life do in extreme environments? She is a graduate, as an undergraduate of Yale, moving on to Brown for her doctorate. She is now a senior astrobiologist at NASA Ames, as I say, in California. She is an adjunct professor at Stanford. And I first met her at a little gathering a few years ago. We were talking at dinner at Windsor Castle when a number of us were gathered there together, and I think it was a late-night evening discussion that she led, which I thought was so articulate that I resolved then and there in England a few years ago that I had to bring her here to Boston to introduce Lynn to this Boston audience and the right lectures. So please welcome as our first speaker, Lynn Rostov from California.
Very, very kind introduction. And I wanted to say, being in Boston here, I grew up in southern New England in Connecticut, and I had absolutely no idea there were this many people in Boston not interested in baseball. So thank you, all of you non-Red Sox fans. I should say that I have a 6th and an 8th grader, which you'll see both of them in later slides, and even my 8th grader's English teacher takes days off for the Red Sox, and that's in California. So I say I'm particularly impressed that all of you are here. What I'm going to do, although my background's in evolutionary biology, the more time that I spend at NASA and thinking about life really beyond Earth, the origins of life, what life means and so on, the more I really go back to the future and back to, in some ways, the pre-Darwinian world where we're thinking very much about the physical environment rather than competition among organisms. So what I'd like to do is give you maybe a slightly different take on early evolution than perhaps you're used to from what you get in classes today, the sort of classes that my colleague is going to talk about and teaches. And so what I'm going to do is tweak you hopefully a little bit and talk about environmental controls on the evolution of life. So the only way to start this is in the beginning. We're going to cover about, 3.5 billion years in the next 30 minutes. So the answer is, hang on to your seats and fasten your seatbelts and try not to blink. So let's start 4.6 billion years ago with the formation of our solar system. And at the center, of course, we have the sun, the source of most of the energy that organisms on the Earth ultimately use today. And at the same time, roughly, we had planets forming. Whether Pluto was one of them or not, I don't want to speculate, but we certainly know that Earth was one of them. The moon was not there from time dot. The current feeling on the street is that the moon formed when really a sort of Mars-like planet hit what was the proto-Earth. Some people call this Earth Mach 1, which is also roughly the size of Mars. It was an enormous collision. As I like to tell my students, it was the ultimate bad hair day in the history of the Earth. Enormous amounts of material were thrown up. Much of this material from this impactor was integrated into the Earth, and all this dust and debris that came up from the surface of the Earth coalesced. Some of it came back down to the Earth, and some of it formed what we see as our moon today. So that was about 50 million years or so after the formation of the Earth. Well, at some time later, we don't know exactly when, the Earth became heavily infested by living organisms. It may have been very quickly after this 4.5 billion year bad hair day when the moon formed. It may have been quite a bit later. We don't know. We do know from the fossil record that life was well established about 500 million years later. But there's increasing evidence that there was liquid water on the Earth almost immediately after the formation of the moon. This is an enormous surprise because we thought that there would be a huge period of time where the Earth would have to cool down before there could be liquid water rather than all of our water inventory in the form of steam. So it's possible that life arose very quickly. I've been sort of teasing my colleagues because they talk about huge amounts of time. They say, well, it takes 50 million years for life to form or 500 million years. And the answer is no one has any idea. And so I've been starting to tweak people and say, well, maybe it was a long weekend. Maybe it was Columbus Day weekend. You don't know for a fact. Maybe in a few years we're going to send our students home with a little kit on Friday and say, make the best life you can, bring it in Monday, and I'll grade you Tuesday. We don't know for a fact. But we do know that within 500 million years, the Earth was heavily infested with life. There's some cyanobacteria. What I'm going to do is sort of get you a few shots from the sort of field work that I do as a way to, take you out of the Boston area. These little fellows live in Yellowstone National Park, where we've done quite a bit of field work over the years. Those are cyanobacteria. They're our friends. They're the ones that are responsible for polluting the Earth with oxygen in the beginning. Okay, let's start sort of then from where we have this planet Earth. We have a moon, we have water, and we have some prebiotic chemicals. We don't know exactly where they're all from. We do know that we get organic compounds in water coming in even today from the solar system, from meteorites and comets. We know that a certain amount have been formed on the Earth. We don't know the relative amounts. But we're going to say we now have an Earth, we now have a moon, we have a sun, we have some organic compounds, we have liquid water, and we're ready to get going. So at that point, what you have is a prebiotic world. You start to have these compounds that are the building blocks of life, and we'll talk slightly more about them later. We then think there was some kind of RNA world, ribonucleic acid-based world. We think this because ribonucleic acids can both function as genetic material as well as enzymes. We now know that as well. It was worth 2 Nobel Prizes about 15 years ago. So say we have this RNA world that's encapsulated into these lipoprotein vesicles. Not very difficult to imagine. Picture yourself making salad dressing, not ranch dressing, but vinaigrette. So you got the oil and the vinegar, and you shake it hard, and you got lots of little vesicles, and that's basically what your ancestors were dealing with. I don't really call this the vinaigrette origin of life, but I suppose you could think of it that way. Then from there, the fact is that RNA can do all these things, but proteins are so much better as structural elements. So I say that there was a protein coup. You can think of a great, overtaking of the RNA. The RNA was relegated to its other functions, and ultimately there would have also been a DNA coup. Deoxyribonucleic acid is double-stranded. It's much more stable. It's much better genetic material. But you see these traces of the RNA world through the cells. Okay, that's a very sort of simple, superficial explanation for the origin of life. But let's try to look a little bit more at what that might mean. And this is kind of an interesting thought. There's Carl Woese, who actually suggested this in a paper, although when I confronted him with it, he said, I didn't actually say it like that, but I'm glad you did. So I feel like I now have, at least his blessing to say this. That the very early cells then with this DNA material, RNA, and then ultimately DNA, were passing around. And, I'm sorry to say this in a very, serious, prestigious audience, but the fact is our ancestors were highly promiscuous. All this genetic material was being passed around. You didn't know who was who. You can think of it as sort of the rampant orgy origin of life. But at some point, there's some sort of thresholds being put down, some kind of idea of self, of individuality. And, maybe you don't want to pass around all your nucleic acids, all yourself to others. And so I think that this really is the origin of self, of individuality. And you start to pass your genetic material down to your offspring rather than sharing it with all of your friends, which no longer your friends, they're your whole family. And so from there, we start to think this point of having this great diversity of life. There are lots of microbes, there were dinosaurs, there are plants, there are animals, we have this marvelous diversity. And we could just sort of leave it like that. But now I want to try to put this a little bit in a physical context. And when we say a physical context at NASA, we're not talking about another 2 degrees global warming or, the sun coming up 2 minutes later. We talk about major factors at NASA. We're sort of these grand thinkers or grand nutcases or however you want to think about it. This over here represents the sun. I don't think anyone here will have trouble recognizing this, but I know in some places that I've lectured where they haven't seen the sun for a while, I've had to point this out. This is the sun. Many of you will recognize it as our closest star. The sun is tremendously important to us because it gives off radiation. PAR is just a short term that we biologists use, meaning photosynthetically active radiation. In other words, the radiation that we see as visible light that the plants are able to use for photosynthesis, tremendously important. And the sun also gives out ultraviolet radiation, among other things. These are the two main things that reach the Earth. Now, the sun is a star. Stars burn. As things burn, they become hotter and hotter. So if you take the time and go backwards, if you run the clock backwards, we think that when the Earth formed and when life began, the sun was about 70% as luminous as it is today. So 30% less sunlight reaching the Earth. However, we do know from studies of other young stars that proportionally they put out more ultraviolet radiation. So where it would have been dimmer, the amount of ultraviolet radiation coming out to the Earth may have been roughly what it is today. Now, radiation has to make it through the atmosphere before it gets to the Earth, and our atmosphere was significantly different. If we think that we have problems with an ozone shield now, the Earth was one giant ozone hole when life originated. So much of this ultraviolet radiation and photosynthetically active radiation was making it right through to the surface of the Earth. What we had, we think at the time, was really a carbon dioxide atmosphere. We had a situation, particularly for a couple 100 million years, where we were suffering huge numbers of impacts. The lunar forming impact was the worst of the bunch, but that doesn't mean that it was a whole lot better. These impacts may have been so severe that the Earth could have even been sterilized several times. Hey, maybe life arose on Earth several times and was killed off by giant impactors. Unfortunately, there's no way we're ever going to be able to know, but it's a rather interesting thought. Water chemistry must have been substantially different. I've heard estimates that, for example, the pH of the oceans, the acidity of the ocean was anything from about 5 to 10, which roughly translates to we have no idea. And then this final thing that a lot of people don't think about, we have a 24-hour day. We're used to that. But it turns out that the rotation of the Earth is slowing down over time, and this is because of a frictional interaction between the Earth and the Moon. This is something actually one of Darwin's sons figured out. And so as time goes on, the rotation of the Earth becomes slower and slower. And if there are any students in the audience, I quickly point out this is not going to help you get through your final exams this year. Day length is not going to be substantially longer in our lifetime, but slowly over time, it becomes longer and longer. So again, if you run the clock backwards, when life arose, the day length may have been about 16 or 17 hours. So that's surely going to affect how organisms go about their business. So what we've seen is some major environmental changes. So let's start again. There's the sun. And so I'm going to argue that in the beginning, what organisms really had to focus on more than anything is not competing with their neighbor, but dealing with a physical environment. And when I say physical, I mean the chemical environment as well. So this struggle for existence was against the physical world, and this is still the number one thing that organisms have to worry about. The other thing they have to worry about is entropy. I was delighted that Eric mentioned Schrodinger and the second law of thermodynamics. We would be breaking down if you have a dead organism. Ultimately, they decompose because the energy is dissipating. We're following the second law of thermodynamics. How do we cope with the fact that we would break down? Well, the answer is that we eat. We like to eat because it tastes good and so on, but what we're really doing is fighting entropy. So the next time you feel like having a second piece of cake for dessert, or the second helpings on the potatoes, you just say, I'm fighting entropy. This is what I'm supposed to be doing, right? Okay, so we're fighting entropy and we're dealing with physical and chemical environment. Secondarily, you have to worry about your neighbors, and that's not to say that that competition doesn't go on. It's tremendously important, and the biological aspects are tremendously important of organisms. But again, what I'm going to argue is the number one thing we have to worry about is the environment. So let's put it really bluntly. Are we talking about physical environment, or are we talking about natural selection? And I'm arguing that certainly both occur, but the first of those, the physical environment, is what tends to get lost in the cracks and is tremendously important, particularly if you're going to look for life elsewhere in the solar system. One of the ways we can approach this is by looking at what is needed for life. And this is a slide this sort of slide you might have seen before. We need a couple of things. We need liquid water. We need biogenic elements. That means that we need things like carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, a source of energy, and we need time. And I've already ridiculed that to some extent. We don't really know how much time we need. We know that life didn't arise instantaneously, but we don't know if it's Columbus Day weekend or if it's 500 million years. But we know it takes some sort of time. And so these are sort of the usual things you see on the slide. And so now let me give you something just a little different take on this. What do organisms really need for life? Well, unless you're doing some sort of Star Trek virtual reality, the number one thing is they need a body. They need a physical presence. And I'm going to argue that a lot of what follows in life is because they need a physical body. I'm going to argue further that this physical body is likely to be based on organic carbon, and it doesn't matter whether it's planet Earth, planet Mars, or some completely yet undiscovered planet on the edge of the universe. It's likely to be based on organic carbon, and therefore the top priority for organisms is finding organic carbon and putting it together in a body. In order to do that, you have to fight entropy. So yes, it's a good idea to eat your dinner. And you also have to do other sorts of things to survive. But the number one thing is to have this body. Otherwise, everything else falls by the wayside. Now, why do I say the carbon is so important? I'm doing this as a straw man because I know there's going to be someone in the audience who's going to say, what about silicon? Well, the fact is the carbon is the fourth most common element in the universe. There's carbon up there, nice little molecule, capable of forming a vast array of compounds from methane to DNA. Silicon can form interesting compounds too, but it pales in comparison to the complexity of carbon. Every college teaches courses in organic carbon, in other words, organic chemistry. I don't know ones that teach whole courses on silicon chemistry. It's just not as interesting. And the fact is we live on a large silicate rock, and we're not based on silicon. If anyone would be based on silicon, we would be certainly good candidates. But I think to me what's been an even stronger argument is the fact that colleagues of mine at NASA and elsewhere have looked out into the interstellar medium among the stars, and they find a very similar organic chemistry to what you learn about in a class in college or in high school. So the language that we need to learn about, for those of us who went through all the pre-med classes and so on, the language that we have to learn about in school is not just the language of getting into med school, it's the language of the universe, which makes one start to feel that perhaps that is the universal language of life. And to me, that is absolutely stunning thought, and if nothing else that you remember tonight, that's certainly a good take-home message. So we said that organisms need a body. If you're going to be based on organic carbon, water is an awfully good solvent, and so then you're really finding that almost everything else falls from that, organic carbon and water, and almost anything else you can argue from life comes from there. Obviously, organisms also have to deal with a changing environment. Again, the word environment comes in. You have all sorts of ways of doing that, physiological, morphological, genetic, and so on. But the fact is your body has to stay intact, so it has to deal with the physical environment. You have to leave offspring. Those offspring have to leave offspring. As people say, the only point in having children is having grandchildren. And then you need some sort of continuity. And again, this has to do with the idea that grandchildren are a great thing. Okay, so if we're going to look at the physical environment in life, it's really instructive to look at the actual limits of life. And this is what I do to some extent. It gets me to exotic places on planet Earth. And so what I'll do is to show you a few slides to sort of give you an idea that the envelope of life, as we know it on planet Earth, is far broader than we would have imagined 10 or 15 or 20 years ago. And I bet it's going to be even broader in another 10 or 20 years. And therefore, this gives us an idea of what the range of conditions where life could form on Earth and elsewhere becomes broader and broader. And it really enriches our definition of life. So what we're going to do is turn to these organisms that are known as extremophiles, extremis being the Latin for living on the edge, phile meaning love. So these are organisms that really like to be on the edge. Of course, not all of them, love it. It's not like I interviewed them and said, hey, do you like living in high levels of radiation? But the fact is they can do it. Love is sort of a subjective term. You're not going to want to really read the rest of this table in great detail, so I'm putting up a simplified form just to give you an idea of some of the physical and chemical extremes that we'll talk about. Temperature, that's a very easy one to deal with. Radiation, pressure, desiccation, salinity, acidity, pH, acidity, alkalinity, oxygen tension, chemical extremes, even living under a vacuum or with electricity. And I show you this to give you an idea that there are plenty of organisms that can do all of these sorts of things. So let's go talk about a couple of these, maybe in a slightly different way than what you're used to. Let's talk about temperature for a moment. Now, it turns out that there are a whole lot of reasons that organisms don't like to live at 200 degrees Celsius or minus 200 degrees Celsius. We like to live days like we had today in Boston, which was, just absolutely lovely. You're talking about, sort of low to mid 20s Celsius. Why do we like that so much? Is it just something, an idiosyncrasy of us? Is it because we've evolved to live in New England, or is there something about life? And I'm going to argue there's something about life. For example, the solubility of gases in liquids changes dramatically depending upon the temperature. And for those, I know there are a few kids in the audience, what I suggest you do is tonight or tomorrow take 2 soda cans and put one in the freezer and put one in hot water for about an hour. And then either go outside with them, wait till your parents aren't home, or go into the bathtub and open them. And I can assure you that one of them is going to go pow, and one of them is going to go and the one that goes is going to be the cold one. And that's because the solubility of gases is so much better at cold temperatures. So you think, cold, that sounds great. The only problem with really low temperatures is that water freezes. If you shrunk yourself down to the size of, say, a mitochondrion, or even as tiny as an atom, you would see that when water freezes, it forms ice crystals, and these would look to you like swords that would start ripping through cell membranes and forming an awful mush. So you don't want to be in a situation where there are ice crystals forming, but you don't really necessarily want it too hot. So if you get it too hot, you start to break down compounds like nucleic acids and chlorophyll and proteins and so on. I tell my kids, you can't unfry an egg. Once you denature proteins with heat, that's all she wrote. If anyone can invent an egg unfryer, I think you're well on your way to, if not the Nobel Prize, something else equally good, no doubt. Enzymes have optimum temperatures for activity. So we really are constantly dealing with temperature. And this just brings home the point. All right, now, saying all that, you would think everyone lives at these mid-temperatures. This is about where we were today in Boston. But the fact is that there are organisms that can live well above that temperature, well above the temperature that you would expect any reasonable organism on the basis of what I just told you to live. In fact, we found archaea now that live at 113 degrees centigrade. You would have not only a boiled egg, you would have a boiled egg that you probably wouldn't want to serve for dinner. It would be so nasty. There even have been reports of organisms living at 121 degrees centigrade, but that hasn't been confirmed. There have been organisms that have been reported to be metabolically active at a few degrees below zero, tons of those, fish with antifreeze and so on. There's a report of a Himalayan midge, just bouncing around at minus 17. I have no personal interactions with Himalayan midges, so I can't verify that. However, like I'm sure many of you in the audience, I went to March of the Penguins last week, and it doesn't take a rocket scientist. I love saying that when I work in NASA. It doesn't take a rocket scientist to know that there are lots of organisms that live below 0 degrees. And when I say this in an audience of so-called professionals, what I hear is, yes, but they're cheating. do you mean cheating? Organisms can live at these low temperatures. There's not this rule book, well, it doesn't count if you happen to grow feathers and have warm blood. It's just one more adaptation. So if you start to look at that, we realize there's an enormous range of temperatures that organisms on Earth can be active in, and if we start to look at where they can at least survive, you realize that we can broaden that quite a bit. All you have to do is think about things like in vitro fertilization, sperm banks, and so on to realize that even body parts of humans can deal with liquid nitrogen temperatures. This gives you an idea of what life looks like at these very high temperatures. This is Octopus Springs, which is one of those meccas for microbiologists in Yellowstone. Yellowstone is at a much higher elevation, around 6,000 to 7,000 feet, where Octopus is, and so water boils around 92 degrees. So when you have something over 95 degrees centigrade, it's already boiling. There are organisms alive in here in this source. As the water starts to cool down, you're going below 92, but not a whole lot. Here in this outflow channel, it's about 83 degrees centigrade. And you're welcome to stick your hand in something 83 degrees centigrade. I slipped once in this little outflow channel, and it's only a centimeter deep, but you've never seen anyone take a boot off so fast in your life. It is very, very hot. And yet there are plenty of organisms that live there. I don't know if you can see these sort of pink streamers called thermocrinus. They're perfectly happy at those temperatures. If you start to cool off even a little more, 65 degrees Celsius, that's still awfully hot. You see very rich microbial mat communities. Here you have a channel that's about 75, 76 in the center, and so you don't see any green because chlorophyll breaks down at those temperatures. But the instant it's below about 73, you have chlorophyll able to stay stable, and you have organisms that are photosynthetic. So you see this beautiful zonation. So you can see that there's plenty of life that can live at these high temperatures and do very nicely. And conversely, besides all the penguins, at low temperatures you can see things like, for example, snow algae, things that are called watermelon snow. I took this picture when we did a field trip to Lassen last summer. They must have had quite a bit of snow because here we were in July and there were huge packs of snow. The snow was tinged pink, and the pink color comes from these green algae that have a lot of red carotenoids, which protect them from the sun. I'm not colorblind. These are green algae with a lot of red carotenoids, and you'll see in other pictures organisms that have to protect themselves from high amounts of radiation. Microbes usually produce a lot of carotenoids to protect themselves. Let's look at pH for a second. Probably all of you are thinking, oh, what was pH again? I remember learning about that. pH is very simply the concentration of hydrogen ions, and so the lower the pH, the more acidic it is because you have a higher concentration of ions. At the high pHs, you have a much lower concentration. Neutral is considered 7. The ocean is about 8.2. So when you're getting to 10.5, you're talking about soda lakes in Africa. Plenty of organisms from a diversity of taxa live there. It's very hard to keep something at pH 12 in the lab, particularly a culture medium, but I've been assured by colleagues who work in some of these lakes in Africa that they've measured the pH at about 12. There are organisms there, and therefore there are organisms that live at these pHs, even though they haven't taken them back to the lab. On the other extreme, you're starting to deal in here with things like lemon juice, battery acid, and below, and yet we're finding more and more organisms that can live down to pH 0. Believe it or not, you can go below pH 0. You now can buy fancy pH meters that will go below pH 0. And I'm sure it's only a matter of time before someone reports that they found an organism living below pH 0. Again, here we are in Yellowstone. This is a boiling acid mud bath at about pH 0.5, and yet this is home for Sulfolobus, which is a bacterium. Not my idea of home sweet home, but this is where this organism is specialized in living. Another sort of acid area in Yellowstone, this is in the Norris Geyser Basin region. This nice little stream here is about pH 2.5, nothing like 0, but I mean, hey, that's way down there. Again, remember the ocean's 8.2. Absolutely covered with this unicellular red alga called cyanidium. Again, I'm aware of the fact that that looks green, but it is a red alga, trust me. This micrograph that I took is not a culture, that's a field sample. So it gives you an idea of the density. These organisms are able to grow in the lab at room temperature. They can grow at neutral pH, but they're lousy competitors. When you go out into nature, they're up there at around 40 to 50 degrees, and they're at these very low pHs because that's where they make their home. That's where they're better than everyone else. And there's my daughter a few years ago. This is also the same pH, but here this area is not fed by hot springs in a continuous sort of way. They're little tiny mini geysers coming out, but most of this mat is exposed to temperatures that are much closer to ambient, and so you don't see as many cyanidium. You see this area just absolutely covered with zygogonium. Once again, this is a colorblind situation. The zygogonium looks sort of purplish to you. It's because as it gets older, it makes purple pigment to protect itself from the sun. So again, just the difference in temperature means a complete difference in community. Salt is another area that's very difficult to live in, high salt, and yet there are organisms that, as you can see, oops, I don't know if I'm getting this at all. This is when I always say in the lecture, I'm not in the technical end of NASA. I'm not responsible for the shuttle. I'm only a biologist. Anyway, you can see in the upper left panel, there's salt crystallizing the side of a salt pond where we used to do some work in Mexico. And there are organisms living there, those reddish things right on top of solid salt. There's my wonderful technician, Dana, getting a sample from San Francisco Bay from the Cargill Salt Company. Again, red because of the protection from the sun. There's a spot up in the Andes where we're starting to do some work. Again, very high salt concentrations, very high levels of carotenoids, organisms particularly adapted to this environment. Along with the very high salt, these organisms are also very often radiation resistant and resistant to desiccation, loss of water. Remember, water is tremendously important for any organisms. Bringing up the idea of radiation, here's a pond. I'm sorry I didn't show you an overall picture, but this is about 13-hour drive north of Adelaide in Australia. This is officially the outback, Octopus Springs. Why would anyone drive 13 miles north of Adelaide to go visit this stream? Well, that bubble there is not just any ordinary bubble. It's full of radon, radium, and uranium. This is a few miles from a uranium mine. So these organisms are getting whacked with enormous amounts of radioactivity from down below. From up above, they're getting hit with that really strong Australian sun. So they're having to deal with very high levels of radiation, yet, you can see here from the green and the brown and so on, there are many organisms that seem to be able to do that. And these are some of the things we're studying. We do know that there are organisms like Deinococcus radiodurans that can live under such high levels of radiation, their DNA actually fragments, and then they put it back together like a puzzle. The reason that we worry so much about radiation, particularly ultraviolet radiation, is because our nucleic acids and proteins have peak absorptions in the UV, around 260 and 280 nanometers respectively. So anytime we're anywhere near these levels of radiation, this range in the solar spectrum, it's danger, it's problem. And that's why we worry so much about the ozone hole. We worry so much about getting more ultraviolet radiation in anywhere near that range. And this would be true of any organism in the universe if they're based on organic carbon. So again, a lot of what I'm telling you will follow from the idea that organisms are based on organic carbon and using water as a solvent. Here's another place where we started doing some work last November, the Altiplano. This is up right across the border into Bolivia from Chile, up in the Andes. We're up there at about 14,000 feet. So the level of oxygen is pretty low. Take my word for it, you feel completely winded. The level of UV is very high. And therefore, you've got these organisms up there that can survive the low oxygen, the high UV, and on top of it, there are all sorts of weird chemistries, like here, these boiling mud baths with sulfur deposits, so no doubt they're extremely acidic. I hadn't expected to run into them, so I didn't have anything to sample, but I will when I go back this November. So you have these organisms that are having to deal with very stressful, bizarre situations. Taking you a little closer to home, I did this experiment with a master's student of mine a few years ago, very, very simple-minded, where we put some yeast cells on the roof. Again, we live in the Bay Area. We live not too far from San Francisco. This was at the end of March. So it's, roughly comparable, I would say, to Boston, sort of mid to end of May. And what we did was we took some of the cells and we put them under UV transparent plexiglass. That's the UVT. I'm sorry, Eric, I think this is sort of dying. The UVT is just UV transparent plexiglass. The Mylar has the UVB part of the spectrum taken out, and the OP3 has knocked out all of the ultraviolet radiation. And what you can see there is that the organisms who were exposed to the normal solar radiation, this is just on the roof of our lab, nothing fancy, grew substantially slower than ones that were not exposed to UVB, and even slower than ones that were not exposed to any ultraviolet radiation. So this is a very simple-minded experiment. So then you can start extrapolating to what it would be like if they were out there every day, what it would be like in the middle of the summer, what it would be like in Bolivia, what it would have been like on early Earth, and certainly what it would be like on a place like Mars that has no ozone shield whatsoever. So you can see that radiation is going to control a lot of what we do every day. In fact, I have a lot of data, which I'm not going to bore you with tonight, showing exactly what times of day we start to have to shut down our DNA and so on because we're having to deal with damage from the sun. I'm developing a vision where I really think much of the world outside is cued into the sun, and it's every day. Now, tied in with the sun and radiation is oxygen. Oxygen is the one environmental extreme that we consider absolutely normal because we've evolved to live in an environment with 21% oxygen. We're perfectly happy here, and we don't think of ourselves as extreme. We tend to think of ourselves as normal. But I'm going to argue that this is actually one of the worst environmental extremes, and therefore we would conclude that we're extremophiles too. Well, oxygen, is a great thing. I have nothing against aerobic metabolism. I do it every day myself. It's a wonderful thing. The reason it's so wonderful is it's 18 times more efficient in breaking down glucose than anaerobic metabolism. I'm sure I wouldn't be this size. None of us would be here if our ancestors hadn't figured out how to use oxygen. But that is a very risky strategy. I just showed two organisms there that are aerobes. The one on the left is playing around a little with being anaerobic, but he's a champion bagpiper, so he knows better. He knows that the way to go is to be an aerobe. But the problem with being an aerobe is it's extremely dangerous. And the reason I say that is oxygen's all very nice and water's very nice, but there are a whole lot of reduction products between oxygen and water that are not so nice, like superoxide, anions and hydrogen peroxide, hydroxyl radicals, which I have circled there in the yellow, are the nastiest of them all. These intermediates can break down your membranes, they can destroy your DNA, they're nasty, and so you're really literally playing with fire when you start becoming an aerobe. The quote that I remember and like to throw out is that there are estimates that by living and breathing, that your average couch potato every day has 17 hits of oxidative damage in every cell in every cell in their body that needs to be repaired. Now, that's being a couch potato. That's not even including getting up, having breakfast, going swimming, or anything else. So this is something, again, we're not aware of, but our bodies are acutely aware of. Oxygen is dangerous. It's a great thing, but we better be prepared to deal with it constantly. And again, to say, I do a lot of work out in the field trying to figure out what organisms are doing in their physical environment. And I got the opportunity to show one data slide, so I will show it, where we've taken some of these microbes that live in this case, Niv Creek in Yellowstone, and looked to see what would happen if we started increasing the level of oxidative stress. And we find that with a little extra oxidative stress, there's actually an increase in mitosis, and that's what you see in the top there. The cell numbers go up. So what we think is these cells are trying to outrun the damage by making a lot more offspring. And you can see from the lower two slides that, in fact, they're feeling the damage, but at these low levels, they're trying to outrun it. Now, at the higher levels, they shut everything down. They try to figure out how to just fix the damage to survive, and if you give them enough, of course, they go to algal heaven and all that. And so let's try to put this whole big picture together, at least for UV and oxygen, because I've given you so many variables it would be very difficult to graph. We got the formation of the Earth down at the bottom there at about 4.5 billion years ago. You've got the oldest rocks coming in. We know that there's water very early on. We don't know if there was life because of the bombardment period, but we have oxygenic photosynthesis taking off fairly early. All sorts of organisms coming about, huge variation in the microbes up to near the Cambrian explosion, probably a little bit more. So most of the history of the Earth has really been dominated by microbes. You see at the very top things like multicellular organisms. You see the starfish there, dinosaurs. At the very peak of evolution, you see the NASA logo, because that's how I get paid to put that in. So anyway, you see all of that. And at the same time, superimposed on it, you see a change in our atmosphere. We've always had enough CO2 to protect ourselves from the very dangerous levels of UV radiation, everything below about 200 nanometers. But as time went on and as the oxygen levels rose, thanks to cyanobacteria, algae, and plants, the UVB portion of the spectrum started to fade off, and so we have really very little left. So all of these organisms, all this evolution that went before was going on in this very harsh ultraviolet environment, plus all the problems with desiccation and salinity and pH and everything else we've talked about. And then if things weren't bad enough, like I say, the day length has changed. So our very earliest ancestors were having to do all these things in a very rapid period of time because they're dealing with 16-hour days instead of 24-hour days. So let's just conclude by looking and seeing what this might mean for life beyond Earth. I gave a lecture yesterday in the Midwest, and so I'd leave this slide in. This is Iowa. Iowa's the moon, Jupiter. Anyway, it's great. I actually gave my students extra credit last year for coming in with Astrobiology Cartoons, and that's sort of a no-brainer way to get extra points. So let's look just simply at our inner solar system, because as I argued, I think that we would see actually the same thing in the rest of the universe, and I don't think it's because of a lack of my own imagination. I think it's because we believe that life would be based on organic carbon and water. If you look right in close to the sun, you see Mercury. Actually, you don't see it because it's so tiny, and I tried to put these in relative size. Prospects for life on Mercury are rather dim. One side of Mercury is constantly facing the sun, and it is, really nasty. It's the place from hell. The other side is extremely cold. There's probably 2 meters worth of, sellable property in between the two, but the waterfront view is rather grim. So we're going to move on from Mercury to Venus. Venus is our twin that went bad. It had a runaway greenhouse. So at this point, it's extremely inhospitable. It could have had life early on. At this point, it's got serious amounts of acidic atmosphere, acidic vapors, and some water vapor. Now, there are people in the last few years who have seriously suggested there are organisms living at a certain altitude in the clouds above Venus, and they have some spectroscopic data. This is not widely accepted, but that idea is out there, and I'd be remiss not to at least mention it. The third rock from the sun, of course, is planet Earth. We know that there's plenty of life there. So let's move on to the little red dot. That's Mars. NASA's been using the approach of follow the water. We do know there's plenty of water on Mars. At this point, we don't think it's liquid. We do know there's plenty of ice in the polar caps. There are people who firmly believe there may be hydrothermal systems, in other words, water systems beneath the surface on Mars that could, in fact, contain life. They're protected from the ultraviolet radiation and so on. I've showed you organisms living in evaporites. We now know that there are evaporites on Mars. These organisms would be protected from the sun. There wouldn't be a lot of action, but there'd be protection. And there are people who believe that there could be small pockets of water on Mars today. And I'm very flattered to be asked actually to propose for a mission in 2011. So, maybe I can come back in 2012 and give you a firm answer. But I think that there certainly is a possibility. And so moving from there, we've got Jupiter. Europa is a moon of Jupiter. We do know that there's liquid water beneath the surface. It's a really likely place for life. The bad news is it's expensive. It takes a long time to get there. And oddly enough, NASA is not really big on large, expensive missions at the moment. But we keep our fingers crossed. And it's been back and forth on whether we have a JIMO mission, the Jupiter Icy Moon Orbiter. Next to there, you've got Saturn. Titan has been in the news a lot this year. It's an organic chemistry lab par excellence. Tons of organics, other solvents besides water, but extremely cold. So this is really more of a frozen chemistry lab. I tell the students, no reputable scientist suggests that there's life on Titan today. And then Francois Roland from the French and collaborating with ESA says that you can't completely rule it out. So there you go. But the fact is that what we've done is we've taken all these ideas that I've given you about the physical environment of life, applied them to our solar system, and again, beating this over and over, I think that we could apply the same sorts of things to the rest of the universe. And that just says what I just said before. So what does this mean? What it suggests is that organic chemistry is the language of life on Earth and appears to be the language of chemistry in the universe. And so therefore, if we replay the tape, there are going to be certain things that will happen again. We will have organisms needing organic carbon. Some will figure out how to make their own, like photosynthetic organisms do on the Earth today and other autotrophs. Some of them will figure out the cheap way to get a meal is to eat the organisms that make their own organic carbon, and so on and so forth. And you have a repetition of this kind of food web and these kinds of organisms. And so the implication is that we don't bother to look for truly exotic life forms. So that pretty much is concluding what I have to say. There are limits to life, and they're connected with the fact that we're based on organic carbon and liquid water. And the number one thing that we have to deal with is having a body that has to have some sort of permanence in face of entropy in the physical environment. This envelope for life is far beyond what we ever imagined it would be. And that some of these adaptations to living then on the edges are very simple. I didn't discuss that in any detail. Some of them are very complex. But the point is that for every one of these, we see multiple organisms from multiple taxa having figured out how to make it in these environments. So what we're not saying is that, yes, there are these organisms from Bolivia that are found on Mars or anything like that, but we're just saying that there's nothing about life per se that precludes it from living in those environments. And finally, we're finding an increasing number of habitats where this could work. And so before I hand this over to Jim, I'm going to finish with this slide, that the picture's pretty bleak, gentlemen. The world's climates are changing. And I point out that's the environment. Number two is the mammals are taking over, competition. And then we have the brain the size of a walnut, and that's biology. And that's sort of where I feel right now. So thank you very much, and pass it over to Jim.
Very good.
I had coffee this morning with several of my graduate students, and I was just telling them what was going on this week. And I mentioned, oh, by the way, I'm giving a talk at the Boston Museum of Science tonight. They said, oh, what's the title? So I'm speaking, my title is The Origin and Evolution of Life on Earth. And they said, well, how long are you speaking? And I said, well, about 30 minutes. And they said, wow, that's pretty impressive. And I said, don't worry, I'm actually one of two speakers. I'm only doing half of Life on Earth. So I'm going to take a different tack intentionally from one that Lynn did. She very nicely emphasized the role of the environment in setting the stage for the evolution of life on Earth. And that's a very appropriate one. Certainly the environment, considerations about the role of the environment in shaping the evolution of life have been paramount. Natural selection to many people is mediated by the environment, or for a long time in the study of evolutionary biology, there's been a belief that natural selection is mediated largely by the environment. But I'm also going to take a slightly different approach, and I'm going to, by not denying anything that Lynn said about the importance of the environment, I hope to at least prove to you that there's another side of this coin, and that internal features of organisms also play a very important role in shaping evolution, and one that until, about 15 or 20 years ago was largely neglected and has become very important in more recent considerations of evolution. Now, that's the central of the three topics on my agenda tonight. The first one, though, I'm going to start off by just describing for you, give you an overview of current studies of phylogeny, the study of evolutionary relationships of organisms. This is something that certainly has been considered for a long time, but it's been in the last 20 or 25 years where there's been an extreme attention following breakthroughs in a variety of sorts, ranging from molecular studies of relationships of organisms, computer analyses, and so forth, have enabled, like no time in the past, the development of a comprehensive tree of life for all organisms on Earth, something that is still very much in preparation, but is being really studied tremendously at present. And then finally, I can't, as I told Eric the other day, I can't, when I'm giving, as an evolutionary biologist, giving a public lecture on biology and evolution, there's the idea of intelligent design is something that has been so much in the news today. I couldn't let this opportunity pass without making my own little comment about intelligent design. So at least briefly, I'm going to try to articulate what I view as the fallacy of intelligent design. Now, let's go back to phylogeny and building the tree of life. As I mentioned just a moment ago, in recent years, there's been a tremendous increase in our detailed understanding of evolutionary relationships and the history of life. People have been interested in this problem for an awfully long time. But due to a number of conceptual breakthroughs and technical breakthroughs in the last several years, there's been a real refocus on generating explicit schemes of relationship among organisms. Why this is so important is that this information allows us to make specific and testable predictions about both specific events in the history of life and the evolutionary mechanisms that are responsible for it. In fact, so much, I presume most of you are U.S. taxpayers, at least those of you who are old enough to pay taxes. You're paying for a lot of this activity, by the way. Here is a front page of a brochure that was published a few years ago by the National Science Foundation, which created a new program, I think it's, well, about 3 or 4 years ago, called Assembling the Tree of Life. The U.S. is contributing to this. This is actually an international program. A lot of other countries are contributing to it. All of the activities are intertwined and interrelated with one another. And it has an extremely ambitious goal to come up with an explicit depiction of the relationships among all species of organisms on Earth. Now, let me try to illustrate to you what goes on here. Now, here we have, I've randomly chosen four species of mammals. Here is, so for instance, a rabbit, and a rat, and a mouse, and here is my boss, President Summers. Now, I can tell this is a nasty crowd. You have to promise me none of you will tell anybody back at Harvard that I'm doing this. Okay, this could get me in tremendously hot water. Now, let's say we wanted to understand the relationships and schematically depict the relationships among these 4 species. How would you do it? Well, the way that people do it, professionally speaking, is to link up pairs of individual species or groups of species at a time. So just scanning these 4 species, which ones would you think are most closely related? So for instance, let's take the rat. Is the rat most closely related to the rabbit? Is it more closely related to the mouse? Or is the rat more closely related to President Summers? Now, you have to tell, you can't say what you'd like to be the case, but you have to tell it. In fact, we know that the rat and mouse are most closely related among these 4 taxa. They are sister groups. And we know this. Traditionally, people have worked out these relationships based on morphological or anatomical similarity. In the last 30 or 40 years, people have been using with increasing success molecular comparisons to assess the degree of similarity, difference, and relationships. And then, okay, so now we have these 2. These are, in fact, are in an order of mammals, the rodents. What is the next closest relative to these 2 species? Well, it turns out it's this one. It's the rabbit. The rabbits are in their own order. The lagomorphs right here, and so they are then closely related. And finally, when we want to come out to the primates, that's where primates hook in. Now, this is a very simple schematic depiction, but it's extremely powerful because it tells us several things, and it especially tells us more things when we add a time axis to it. So moving from left to right, we see that these 2 species are most closely related to one another among the 4. These 2 are then most closely related to this one. These 3 are then most closely related to this one. That's working from left to right. What if we work from right to left? This is earliest time back here. This is the most recent time up here. Well, this tells us, this line here represents a common ancestor, a sequence of ancestors and descendants that all of these 4 species have in common at a very distant time in the distant past. At this point, this represents a branching event in the history of those groups, a time when there was a split, and this line ultimately led to the evolution of Homo sapiens and its relatives, whereas this line led ultimately to the evolution of rabbits, their relatives, and to the rodents. There was a period here when these 2 groups had, excuse me, Eric, I'm not a rocket scientist either. Let me try this other one. Okay. When these 2 groups had a common ancestor, here it is. Then there was another split right here when the rabbit's lineage evolved independently of the rodent lineage. And then there was the common ancestor here of the rodents. And then there's another evolutionary split in which this line gave rise to the rats and their relatives and the mice and their relatives. So we have a series of common ancestors. We have a series of branching events. And what one can then do is take this information and superimpose it different features, characters of these different groups, and make predictions and hypotheses about how those characters evolved. So, for instance, we could look at this bunny and say, when did hopping evolve? Well, one possibility, we could conjecture that hopping evolved way back here, and it was found in the common ancestor of rabbits and rodents. Well, if that's the case, and the fact that these rodents don't hop, that means that the hopping was lost along this scheme. Alternatively, hopping could have evolved on this particular lineage right here, independent of anything that happened here. Likewise, one could ask, well, when did long tails evolve? Both of these species have long tails. That suggests that their common ancestor had it back here. But maybe this common ancestor had it as well. Maybe this common ancestor had it as well. And this is basically what many evolutionary biologists do for a living, is test these hypotheses of the evolution of characters. At the same time, they're using those characters to build phylogenies. Now, that previous illustration had 4 species on it. This is an illustration that's prepared by a colleague of mine, David Hillis, at the University of Texas. And one of his research goals is ways of depicting phylogenetic relationships among organisms. This is the same kind of a scheme that I just showed you, but instead of 4 species, there are 1,000 species. It's very difficult, of course, to represent 1,000 species in a linear sequence, so instead what he's done here is, in effect, depict the species in a circular manner. So all around the periphery are different species. Here are the different lines that lead to them, and there are the different representing common ancestors and branching points and so forth. Now, I'm going to have to allow me one moment, get out of this, and go here to this. Here's the illustration, and what I'm now going to do is just start enlarging it. And as we're going along, you'll see. Hold on a second. If you can read the writing here, it says animals here, and then it says plants over here. And I'm just going to start enlarging this particular part of the tree. This is an extremely big file, which is why it takes so long to do this. Now, those of you who have extremely good eyes can start to see what it says right here. So as we enlarge, this particular region of the tree is coming into focus. I showed this to my class the other day, 500 students. There was thunderous applause when we finally got to this point. They found it very reassuring. So here we are. There is Homo sapiens. There are humans. There is Mus musculus. That's the mouse. There's the rat. There's the rabbit. And in fact, you can see the rat and the mouse are each other's closest relatives. And we can go a little further out in the tree here. Let me see if I can do this. Anyway, so now here we have rabbits hooking up to the rodents, and then further out, these 3 groups would hook up to Homo sapiens. Now you might ask, well, what are some of our other immediate relatives that are represented on this tree? Well, if we go in one direction, here's alligator mississippiensis. There's an alligator. There's a robin. There's a chicken. There's a snake. There's a lizard. There's a lizard. Going in the other direction, this is our amphibians over here. This is a frog. These are frogs. There's salamanders farther along here, and so there's a lot of fishes around here. So this is an interesting way to depict evolutionary relationships among organisms. Now, there are right now 1.7 million species named on Earth. The estimates of the number of species that actually exist range wildly from 3 to 4 million up to a really outlandish estimate, but I guess conceivably could be true, of 100 million species. If we assume, which I think is a conservative estimate, that there actually are 10 million species of organisms on Earth, of which only 1.7 million are described, it would take 10,000 of these trees to depict that. But in fact, this is what is being done now, is people are attempting to work these out and also develop the computer graphics capabilities to make these depictions. Now let's go back to my other presentation. Now, in fact, if any of you are curious in following this up, you can go on the internet. There's a site readily available. It's freely, publicly available. It's called the Tree of Life Web Project. Or you can choose your favorite particular group of organisms, and it will tell you what there is known at present about the relationships of the species within that particular group or those species to other groups of organisms. So now let me move on with that information in hand and discuss the role of intrinsic features. And again, as I said a few minutes ago, my point here is that there's been a gradual appreciation in the last 20 or 30 years that there is more to evolutionary biology in terms of the understanding why evolution occurs the way it does, the direction that organisms go as they evolve. There is more to it than just the environment. Environment is critically important, absolutely essential. But environment in and of itself is not the entire explanation. So what do we mean by intrinsic features? Well, we're talking about features of anatomy, among others, features of anatomy and develop that can mediate evolutionary change. And what these features do is sometimes they reinforce, whereas other times they may actually oppose environmental effects. In some cases, channeling evolution in certain directions. In other cases, constraining evolution, preventing evolution from going in certain directions, even if the environment is trying to select for things to go in that direction. Now, I said that this is a recent idea. In fact, it's in its basic essence, it's not an original idea. It's not a recent idea. It's permeated the history of evolutionary biology for a long time. Perhaps the most sensational example was originated by this man. This is Ernst Haeckel. Ernst Haeckel was a sensational German biologist of the 19th century. He was an absolute champion of Darwin, and in fact, a much more popular and successful popularizer of Darwin's ideas than Darwin had ever hoped to be. Ernst Haeckel did a lot of things. Among others, he coined the famous so-called biogenetic law. The biogenetic law you may have heard of. It goes by the name ontogeny recapitulates phylogeny. Now, what was Haeckel trying to get across? Well, what he was trying to get across is represented in these illustrations. This is a very famous illustration, quite a sensational illustration, in fact, taken from a textbook that Haeckel published in 1874. And what he's representing across this illustration, first of all, is each of these columns represents the series of developmental stages from early in development through the middle time in development to later development. These are all embryos of an individual species. And reading across the chart from left to right, we have, this is a fish. Here I'm having trouble seeing it. This is a fish. This is a salamander. This is a turtle. This is a chicken, thank you. I do know what a chicken looks like. It's the angle, you have to understand. This is a pig. This is a cow. This is a dog. And here is humans. What ontogeny recapitulates phylogeny said is that in evolution, new features can only be added on the end of ontogeny, the end of development. And when you have an evolutionary series of ancestors and descendants, the descendants recapitulate the developmental pattern of their ancestors and then add a new feature on at the end. And what he was trying to get across is shown here, is as you look back in time, according to a literal belief or translation of Haeckel's ideas, these earlier stages of ontogeny, of the development of a single species, would have corresponded with adult stages of ancestors. Now, in fact, just looking at this, it's ridiculous. This clearly can't be the case, but people believed it nonetheless. And in fact, even Haeckel had to come up with a series of rationalizations and explanations why, if you actually looked at embryos, that's not what you really saw. What you really saw did not mirror what his theory suggested, but he nevertheless believed in his theory. Now, this was the most extreme elaboration or exposition of an internal feature driving evolution. It said that no matter if there is an advantage for some new feature to evolving or appearing early in the ontogeny of a species, it simply cannot happen. It can only be added on at the terminus. Now, this illustration is an extremely famous illustration because it has been reproduced over and over and over the decades in textbooks, in magazine articles, because it's a real icon. It's a very famous illustration in the history of evolutionary biology. A few years ago, I collaborated with a British scientist named Michael Richardson, and it was Mike's idea, not mine, to actually go back at those species and look at the embryos and see what they actually look like. And when we did this, we found that the early stages of embryology of those species, in fact, did not look identical, one species to the next. And in fact, each species had a very characteristic pattern of ontogeny. Each species had a characteristic embryo all the way back as just about as early as we could see it. Now, what we have here is an illustration that's basically represented the same way as Haeckel had done. We have many more species across the bottom. These are a number of fishes across the bottom here. You maybe you can read some of these. These are salamanders here. Here's a snake. There's a chicken. There's a possum, cat, bat, and a human. So these are the latest embryos. These are intermediate stage embryos. These are the earliest stage embryos. We found that ontogeny, while highly variable, ontogeny was highly variable among species. Evolutionary features, evolutionary innovations can occur early in the history of ontogeny. However, I was very shocked when about a year after this, after we published the article, there was a firing line debate, this great maybe PBS show you may remember by William Buckley, a firing line debate about creationism versus evolution. Several of my colleagues were on the evolution side. I only knew one of the people on the creation side. And I was shocked as I'm watching this debate, and all of a sudden somebody on the creation side holds up an illustration from our paper saying that we have now disproved evolution. So that's why I'm saying here that ontogeny, while highly variable, nonetheless provides abundant evidence of evolution. Yes, we disproved or we showed that Haeckel had misrepresented his embryos, but in fact, the evidence in support of evolution has never been stronger. The more studies of embryology and developmental biology are done, the more evidence in support of evolution is gained, not the less. Now, in order to pursue this, let me bring this to the modern day. I'm going to take you on a brief field trip. Here is a very famous landmark in southern Mexico. This is Mount Orizaba. And I've got a picture of it here because this is where I do and my colleagues do a lot of field work. We look for salamanders throughout Central America because we're interested in studying their evolutionary biology. We're also interested in describing new species, of which there are abundant numbers. Mount Orizaba is a very important landmark because it's the highest point in Central America. It reaches an elevation of about 17,000 feet. And if you were to go on the mountaintop on the volcano right here, as we've done, you would find there's salamanders living in these forests. If you look right here in these forests in the foreground, you also find that there are salamanders. Here's another spot not too far away. This is a very dramatic landscape. This is right at the edge of the Mexican plateau. The Caribbean is off in the distance here. That's why there are all these clouds. It's an extremely humid area. The moist winds come up and the clouds form here and they drop tremendous amounts of rain. At the periphery, we look around in these forests which rim this valley right here. Is a very beautiful spot. Here's a picture of my colleagues, just to show you where these things are found. This is David Wake, my former major advisor in Berkeley. We look for these things these salamanders in bromeliads. They live here in the base of them. Gabriela Pata, former postdoc of mine, a Mexican scientist, is showing we dig in the road cuts and we find them terrestrially and buried in the vegetation here. Now, what are we looking for? We're looking for these things. These are salamanders. This is a particular kind of salamander that's only found in southern Mexico. I've got to admit, as much as I love these things, these are not the most flashy animals as animals go. In fact, that's about as flashy as they get. Those are four species. They all look pretty much identical. What is most interesting about them, though, is captured for you here. This is one salamander not sitting on a banana leaf. This is a salamander sitting on a blade of grass. These are extraordinarily tiny animals. These are adult animals. And what this animal, it's called Thorius. The name of the genus is Thorius. Here's one. They represent a very interesting evolutionary phenomenon called miniaturization, the evolution of extremely small body size. And what we're showing you here is a large salamander. This, in fact, is a very large salamander, also found in Mexico. This one is about 140 millimeters, so let's say between 5 and 6 inches from here to here. Add another 4 to 5 inches for the tail. You have a salamander that's about 10 inches long. And you have a tiny Thorius here, which is 13 millimeters, about a half an inch from here to here. Add another half or 3/4 of an inch here. So you have an animal total length of a little more than an inch. They've clearly evolved from very larger animals. but they are, in fact, an example of a phenomenon that one sees over and over in the history of animals, the evolutionary history of animals. Evolution of extremely small body size, and what seems to be so important about it is if we look in the history of many different groups of organisms, it seems that they evolved, these individual groups evolved from very tiny ancestors. There's something about small body size, extremely small body size, that facilitates the appearance of novel anatomies, novel body plans, which gives rise to entire taxa of animals. So, for instance, snakes are believed to have evolved from very tiny ancestors. Turtles are evolved from very tiny ancestors. So for a lot of other invertebrate groups are believed to have evolved from very tiny animals. So there's something about the evolution of extremely small body size, miniaturization, and the appearance of novelty in evolution. Now, we're also interested in not studying just the anatomy. I said we're inventorying the species down there, so just let me give you an idea of how many species of this group there are, and also emphasize the idea that I suggested earlier, is that while we tend to think we've inventoried many of the species of living species on Earth, and we have, there are tremendous numbers of species that remain undescribed, remain still to be discovered today. So here is a scheme just showing you a lot from left to right. This starts out in 1869 when the first species of Thorius was named. Here it is. Then between 1940 and 1970, there were another 9 species named. Here they are. You don't need to worry about these names. And these earlier species were described simply on the basis of anatomy, anatomical features. I started doing my dissertation. This is a group I've worked on for an awfully long time. I started doing my dissertation in the 1970s, and I started using at that point some molecular assays. These are proteins, allozymes, which are very effective for telling apart and identifying new species. And I and my colleagues discovered all of these additional species, and these are all the new species names that we've come up with. I had a hiatus of many years, and then when I came back to Harvard a few years ago, I started going to Mexico again. Now we're using DNA sequencing, and each trip we go down to Mexico, we find another 1 or 2 species. In fact, we're finding new species so fast, we can't name them fast enough, and that's why we just have numbers for many of the species. It takes a lot of effort to describe a species. So each time we go, we can find new species. So now it's a pretty diverse group. And we can then take this information and do molecular analyses on these species and build a phylogeny, just the kind that I showed you earlier, only for 4 species of mammals. And that's what I'm depicting here. First off, I'm just showing you gradually the species that were described over time. So here's the initial species that was described in 1869. Shown in green are the ones that were described in the 1940s to 1970s. Shown in blue are those species that we discovered in the 1970s and the 1980s. And here in red are the species that we've discovered since the year 2000. So we've been able to produce a phylogeny, a scheme of phylogeny, as people are doing for just about every group of animals and plants that they can find these days. And we can now use this scheme of relationship to test and assess the evolution of particular features in the history of the group. Now let me now digress to another very interesting aspect of Thorius. Here is a head of an adult salamander of this group, in which this is a very common anatomical procedure where we take the specimen and we immerse it in a series of dyes. And it's very much like dyeing Easter eggs. There's no other way I can describe it. First, we put it in one dye that stains bones red, and we put it in another dye that stains cartilage, the soft skeletal tissue in your ear, in your nose, and in your ears, blue. And we can make the rest of the animal transparent. And that's what we have here. This is a head of Thorius. The total length from here to here is 3 millimeters. This is an extremely tiny head. And here you have the nose. There's the eye. There's the inner ear. The brain is transparent. It's behind the eye. Here's the lower jaw, and so forth. This is the first vertebrae. Now, I'm calling this unintelligent design. One of the the fundamental premise of the argument of intelligent design is that when one looks at nature, one only sees perfection. One only sees, I'm going to emphasize, I'm going to exaggerate it to make a point, but I still think it's a valid point. One only sees perfection. One only sees perfect design. One only sees complexity. One never sees imprecision or sloppiness and so forth. Well, in fact, in my view as an anatomist who studies a lot of these things, in fact, there are tremendous numbers of examples in nature of anatomical design that are simply bad. They're sloppy. It's astonishing that the animal remains alive. Thorius is a great one. Let me just show you. Now, here's the front end of the skull. Bone is red. There's hardly any bones left in this animal as an adult. Here's one bone. This is the maxillary bone. This is the bone that corresponds with your cheekbone, or the one that holds a lot of your teeth on your side of your head. Now, where does this bone connect to? Nowhere. It stops. It's hanging out in space. In the front, where does this bone connect? It doesn't. There's a big gap. Where does it connect above? It doesn't. This bone, this main what is typically a tooth-bearing bone, is sitting out floating in space in the head. There's another bone here, which is so reduced, it's so tiny, it's just sitting here. It's floating by itself. There's another one over here. There's another one over here. This is an extremely weird skull. You would never, ever design a skull like this. I'll show you another picture in a moment that shows you the skull in the roofing part, the part that overlies the brain, has literally a big hole in it. It's a hole in its head on the top of a skull. That's an absolutely characteristic feature. Now, there's another feature is the very enormous eyes. Look how big this eye is in the head. Look how big this inner ear is in the head. Look how big the nose is in the head. What's going on here? Well, it's hard to explain from the standpoint of an intelligent design, of a perfect design, but it's extremely easy and straightforward to explain from the standpoint of evolutionary biology. And it has to do with how you evolve a small animal. If you think about it, there's not too many alternatives to evolve a small animal from a large ancestor. The most obvious, or one obvious way, is that a descendant simply stops growing at a small size and becomes sexually mature. If it stops growing at a small size and becomes sexually mature, it retains a juvenile anatomy, or even an embryonic anatomy. And in fact, that's just what we have here. These bones are in an embryonic state. In a larger salamanders, these bones would form early in the embryo or in juveniles, but ultimately would continue to grow and reinforce the skull and form a real structurally integrative structure. That's not what we see at all. This animal is basically a sexually mature juvenile of a larger species. Now, another thing that's going on has to do with, let's just take the eye. You can only reduce the vertebrate eye so much before it doesn't work anymore. What does an eye do? An eye focuses light on the retina to make an image. We can already tell that something weird is going on with the eye. Here's the lens inside the eye. The lens is disproportionately large. And in fact, if you were to look inside this eye, do it in serial sections as we've done, you'd see that there's almost no space between the lens and the retina. This eye is about as small as you can make a vertebrate eye and still function. What has happened is, as small size has evolved in this group, as these animals have gotten smaller, the sense organs have gotten disproportionately big simply because they cannot function at a smaller size. You cannot select for a smaller eye because it would not function. So internal features, internal relationships, anatomical features, functional relationships are dictating the direction that evolution can go. As small size has evolved, the sense organs have gotten disproportionately large, and the skull has shrunken around the rest of the skull, the rest of the head. Now let me reinforce this by looking at a different species. This is perhaps my favorite Thorius, Thorius aureus. It's called, you kind of get desperate for names of these things. We named this Thorius aureus because it has a gold stripe. Thorius aureus is a very unusual species because it has, now here, this is an X-ray of a Thorius, a very sophisticated kind of X-ray. I'll show you in a moment. This is a skull of Thorius aureus. There's the hole that I was talking about, or this is a label pointing to the hole in the skull. Thorius aureus has teeth on the maxillary bone. That's very unusual. Most species of Thorius don't. Thorius aureus, when we discovered this species, we said the fact that it has teeth and the fact that it has a hole in its skull, but a very small one, we assumed that this was the most primitive species in the genus, because other salamanders have maxillary teeth, and we assumed Thorius aureus retained those maxillary teeth from its ancestors, and it simply hasn't lost them as other species have. Now, let me just show you. This is a very, very impressive kind of an X-ray where you can actually do three-dimensional views of it. So we're going to just rotate the skull, and you can see as we're going along here the hole in the skull. There it is right there. And if you were to look carefully, you can see they're very tiny. There are teeth, tiny teeth on this bone right there. I'm going to stop this and move on. Just show you this in a different view. It's a lot smoother and a lot faster. Again, this is the animal showing you that dorsal hole in the skull, which is the smallest of many other species, and the fact that it has teeth. Now, we then traced the evolution of teeth in this species, and we did this on this phylogenetic scheme of phylogeny. Here we have the same scheme of phylogeny that we were looking at earlier. And these are all the species. We don't need to worry about the names. These are two other genera of salamanders that are related to Thoreus. And what I've done here is color code the branches according to our best understanding of whether these species had teeth or not. Red means they have teeth. Red means they have teeth. Black means they don't have teeth. Yellow means some of the adults have teeth. And we've then filled in the lines here to give our best estimate of the evolution of this particular feature. So it's logical that the common ancestor down here had teeth, and then teeth were lost subsequently in Thoreus. Now, where's Thoreus aureus? Here's Thoreus aureus, which has teeth. I told you when we first discovered this species, we assumed this was the most primitive species in the group, and that the presence of teeth meant that it was closely related to these species out here. In fact, that's not the case. What seems to have occurred in the history of this group is teeth were lost at the base of the phylogeny, and they were regained. They were re-evolved at this point in Thoreus aureus. But not only that, they were re-evolved independently several times at different parts in the history of the group. And teeth were then lost independently at another part in the history of the group. So we see that the evolution of that one particular feature in the group is not a simple logical trajectory with a minimum number of steps, but in fact it's a much more chaotic pattern with a series of gains and losses and regains and so forth. Now, when we look at teeth in particular in vertebrate animals, we see that the loss of teeth is much more common than gain. In Thoreus, we see an instance of regain of teeth. It's an exceptional case in vertebrates. Now, how common is this pattern of the regain of complex features? People until now have thought it is almost impossible. But one of the things that's coming out now with additional studies, phylogenetic studies, which allows us to make very precise predictions, is that regain of complex features, loss and gain, may be in fact a pretty common occurrence in the history of evolution, something that has not been appreciated very much. Here's an instance that was published in the journal Nature last year having to do with the re-evolution of wings in insects, not just once but many times. Now, let me just say in my last slide here, I just have had a very brief opportunity to touch on it. I'll just elaborate just to a little bit. With respect to intelligent design, the history of life, from the standpoint of an evolutionary biologist who studies animal design, studies animal history, is anything but logical, efficient, and even intelligent. Instead, one sees a preponderance of accident, contingency, inefficiency, redundancy, which are fully consistent with our understanding of evolutionary mechanisms. Unintelligent design is a more appropriate metaphor for what one sees in most of the history of life. Thank you very much.
All right, at this point we will pause for 1 minute. You can get up out of your seats, but don't change your coordinates while we form the panel. Going. All right, excellent talks, no question about it. Indeed. Yep. Two of the very best talks we've ever had here over the course of a dozen years. And now my role as jeune provocateur is to break the ice a little bit here and actually take the advantage myself, selfishly, of pitching a question to Jim and to Lynn, and hopefully pull back a little bit myself and let these two people start talking to each other. And because we will go, I'll say, as Ted Koppel will go, we'll say, we'll alert the local stations. We'll go 5 minutes beyond, till 9:05. And give you an opportunity quickly to enter into this dialogue. So my question to begin with concerns the tape of life. You mentioned it. You mentioned it indirectly. If Stephen Jay Gould, the late Stephen Jay Gould, were here, he would perhaps appeal too much to Jacques Monod, existentialist 1960s France, chance and necessity, emphasizing chance. And Steve always used to say, if you backed the tape of life up and then let it run forward again, because chance was so dominant in his view of natural selection and Darwinism, neo-Darwinism, and the like, you'd probably get a wide spectrum of highly diverse and different species or different anatomical creatures than we now have. Simon Conway Morris, who was with us at Windsor, he had a very strongly held view, very anti-Steve Gould view, that there was a sense of contingent evolution, that chance was not as dominant. If you back the tape of life up and ran it forward again, you'd probably get pretty much, generally, statistically speaking, the same structures of objects that we have now. Speak to this issue of chance and necessity. To what extent chance and determinism, randomness and necessity is playing a role? I don't need you to tell me whether you think Steve was wrong and Simon was right, but you may want to say that as well. But what about the tape of life now? What if we did back it up by hundreds of millions of years, or maybe 3.5 billion years, and then ran it forward again? Do you agree, the two of you, outstanding world-class biologists, what would happen today? Would we statistically be here?
Lynn said it. She should answer first.
Batter up.
To add, as my colleague said, my office is located about 27,000 feet above the face of the earth, and when you put yourself in the hands of the airlines, you wonder whether anything is contingent. But that being said, I argued, I think in the talk, that if you go on the assumption that life is based on organic carbon and on water, there's certain things that do fall from that. I'm not saying that I would be here or we would be here or that butterflies would be here. The specifics may not be there, but there are certain things in the broad outline that you can argue will happen over and over again, simply because we're based on organic carbon. And there's not that much organic carbon in the world. Most carbon is in the form of carbon dioxide, few diamonds on some people's fingers, and so on. But most of it's carbon dioxide, which doesn't cut it. So if you need organic carbon, the clever organism uses what's out there, because sometimes I worry that this is going to be my legacy in biology, the laziness principle. No one does anything unless they have to. And so if there's organic carbon there, you eat it. But some clever organism is going to figure out, well, if I make my own, I don't have to worry about fighting over the dinner bowl. So they start making their own. And someone else figures out, hey, if I eat the guy who's going to all the trouble to make dinner, that saves me some trouble. And then you start to get herbivores. And then someone else says, but the protein content of this guy is even better. So then you get carnivores. And you see these sorts of food webs occur over and over. And I would argue that in those broad outlines, if life is based on organic carbon, which I think it would be, then you would see those broad outlines re-evolving over and over and over.
Would the Evo-Devo approach with its genetic toolkits and its genetic switches?
I would say, I'm going to give you a frustratingly intermediate response, which is that there are certain features of animal design are inevitable. And in fact, this experiment has been played out already in different continents, different groups, and over evolutionary time. Think of a porpoise-like animal. Porpoise-like animals have evolved repeatedly in addition to that which we see today in mammals. In different groups of prehistoric reptiles have produced an animal which, at least superficially, looks very much like a porpoise, but it's not. So there are certain forms which do seem to recur, and they just make sense. They are obvious solutions to particular environmental problems. Could I guarantee you that if we were to replay the tape of life over again, would elephants evolve? I think not, because there are some forms which are so odd, so special.
Speak for yourself.
Yes, I'm told I'm odd. There are some forms that are just so odd and so special. I can't, from what we now know, I can't see why it's inevitable that they would have to be there.
Can I argue with that?
Please, yes, by all means.
This is why Eric's sitting in the middle, I think. But you're starting off with something with certain bilateral symmetry, and that it's got a brain at one end and something else at the other end, and so on and so forth. And so you already have the basic structure of a dolphin. But if you go back even further, you've got things like sponges. Now, why do sponges have to evolve into bilaterally symmetrical animals? I mean, you even have things like starfish that are perfectly good predators that are radially symmetrical. So they're symmetrical in a circle.
I'll just respond to what I told my lecturer a couple of weeks ago. We talked about the evolution of body symmetry. Bilateral symmetry is an indication, when you see it in animals, of motile, actively moving, locomoting animals. You can't be an actively locomoting animal and being a radially symmetric animal. Starfish are they're active predators, but they're active but really, really slow predators.
But jellyfish are pretty fast.
But they're passive. They're passive swimmers. They're not active. To have a really fast swimming animal, you need to have a bilaterally symmetric animal. So if there is any opportunity or a niche, an available ecological, I can't believe I'm taking the environmental side.
It's falling into your trap.
He's tricked me. He's tricked me into doing this. If there is an available opportunity in the environment, that is the only way. You'd have to have that configuration, anatomical configuration, to occupy it. So for that reason, yes, you would evolve it. Bilateral symmetry would have to evolve again.
I'll meet you at the Monterey Bay Aquarium.
We're trying to peel away the veil here a little bit and let you peek into the world of scientists talking to each other. It's not as all clear and clean as the scientific method textbooks would have you believe. There's a subjective side of science. There's some emotion going back, and that's what science is all about. And that's frankly why it makes it so much fun. Laura's over here with a mic, and Cheryl is somewhere over here with a mic. They're right fellows at Tufts, and they're roving around here looking for people who are ready to intellectually attack us. Attack the speakers. Please.
Okay, I'm not sure how much of an attack this actually is, but this is more of a chemistry question. Ma'am, you mentioned in your talk that they found basically nucleic acids out in space just sitting around. So I'm guessing... Well, I guess my question is, why would those then form into molecules, which would then form into organisms like algae or even something simpler? I mean, I guess the why behind it more than just the physical, okay, we want to fill these valences, all right, well, then why would they want to exchange information and thus bringing life?
Okay. Let me explain that we haven't actually found nucleic acids, but we found bases, we found amino acids, polyaromatic hydrocarbons, all sorts of complicated carbon chemistry. We haven't actually found strands of DNA floating out there. But what they do is, in solution, they form these polymers. I mean, that is the fact. You go back to things like the Urey-Miller experiments where they sparked, actually in that case, inorganic compounds, but you could take organic ones, and some of these things form spontaneously, some of them form with a little extra energy. But then I think what you're getting at is why would, say you do get nucleic acid, why would that then be the genetic material? And the answer, and maybe now I'm doing the same thing back to Jim that he did to me, is that that's not necessarily the first thing that you would do, that is a very complicated system. And people who study this much more intensely than I do have suggested that things like glycerols may have been the first genetic information, or colleague Graham Cairns-Smith in Glasgow has suggested that clays may have been our first genetic system. So, think about that next time you play with clay. Our genetics may have started in the mud. So that's sort of a situation where there could have been a takeover then by DNA ultimately, because it's much better than clay as a genetic material for organisms on Earth.
Sherry, where are you? You have a question? Hands? Right here.
Did you want to argue?
Did you want to have a follow-up? No. Yeah, okay, sorry. I didn't think you did. Please.
Yeah, I have a question. Has more to do with the intelligent design debate that's going on now. And the question is this. How do we, as scientists, or people who are grounded in science, explain to people who are not grounded in science, but who are grounded more in emotion, that they're wrong?
All right, how long do we have, Eric?
Well, you could just say that, I guess, but no, I understand. Well, I mean, I'll react in a couple ways. My point is actually different than a lot of my colleagues. People, I think these days when they attempt to challenge intelligent design, they're accepting the premise that design is really impressive all over and so forth, and we have to then come up with alternative ways of explaining it. My contention is that I don't even accept the basic premise, that there's something that needs to be explained. I say if you actually were to look at structure, look at form, you see that the whole fundamental premise is not there. So I think, there's no simple answer. Ultimately, it's a failure of science education, right, in a broad sense, that we are at this point. Now, the challenge then is to make science, and particularly evolutionary biology, sufficiently compelling and convincing that people will just be familiar with the truth, be familiar with the facts, so they can see that there's, and also about how, for there are cases, very marvelous cases, such as the structure of the eye, which is always pulled out as a thing. But there are plausible explanations for evolution of those features, and people just need to be introduced to these things. I mean, at that point, it's up to them to accept or not.
But to emphasize, I think, as you say, the ideas are trying to create a problem where there really is no such problem. In particular, they're trying to create a controversy where there is no such controversy. Really, it's... Pardon?
They're doing a good job at it.
Well, yeah. Lynn?
Can I take those? Eric didn't mention in my CV that I also got my master's at Indiana University. So I feel like I have some battle scars because I taught evolution in southern Indiana for a couple of years. And I had students who tried to save my soul and so on, distinctly unsuccessful. But nonetheless, I think that what we did teaching the class, which I thought was a very clever approach, and it's not new to me, I'd immediately say, but I think it's very clever, is that there are a lot of people out there where it's not really a science question. It's a question about uncertainty, about biblical literalism, about feeling uncomfortable in the modern world. There are all sorts of issues tied up with this. And so what we did is say to the students, and I still do, if you believe in creationism, or you want to believe intelligent design or whatever, because you believe that your immortal soul is in danger, what is an A in my class next to your immortal soul burning in hell? You should do it. Flunk the class. Do what you need to do. That's the priority. But if you're saying this because you're buying these specious arguments that are a complete misuse of science, pull up a chair and let's talk. Let's go back to the 19th century. Darwin said very clearly in his writing that he was completely charmed by the idea of intelligent design when he was a student. Now, what made him change, and not only Darwin, but most of the great minds of the 19th century, not some nutcase in the backwater, but the greatest minds in science at the time went from intelligent design to evolutionary biology, and many of them, but not all, certainly to natural selection. And so what I have my students do is go back through the structure of the origin of species. All you have to do is read the table of contents. That's the dozen pages it is, to look at that structure. But once they sort of put it that way, you don't have to if you're worried about your soul. I found that a lot of the students go, phew, and then they can talk. And so that's my answer from, some battle scars, and take that one for what it's worth.
There's a gentleman up here about midway up with a plaid shirt. Sherry, do you have him? Players up your hand? Yeah, there he is. Laura, you got somebody over there? Okay.
In your talk, you said that ontogeny recapitulates phylogeny. The history of the race is relived in the history of the individual, or the development of that individual. Also, we know that in DNA that we have certain building blocks that are common to different animals, like the homeobox, for instance. Can you describe to us that evolution is not a theory anymore? It's actually a fact that can be established with the new information that we have in the building blocks of the DNA?
Give him a chance.
Yeah, I mean, one of the frustrating things I find as an evolutionary biologist, when people, there are all kinds of controversies in evolutionary biology. People make theories about specific mechanisms, specific events that sound great but are ultimately disproven. That's part of the game. That's the way science works. But nobody on the scientific side is really disputing that evolution is not true. And it's especially frustrating for me because the world of molecular biology, which was developed in the beginning in the 1950s, has added a whole additional class of evidence in support of evolution. The fact of evolution is in support of particular evolutionary mechanisms. The fact that, remember that scheme I showed with the simple phylogeny with the common ancestor. The fact that there are common ancestors makes you would predict that animals that are most closely related would have extreme genetic similarity. They would share particular genes, and that they would differ from the genes of more distant relatives. That's exactly what one finds out. So genetic analysis has only added a tremendous amount of additional evidence that's fully consistent with the idea of evolution by common descent.
Jim, wouldn't you say that there's also a problem in the public discourse of confusing evolution, change through time as a fact, and natural selection as a mechanism?
As a mechanism.
Yeah, the basic evidence when there has been descent through time, it's abundant. It's everywhere you look. It's in fossils. It's in relationships among organisms. It's in DNA. Where the debates center is in explanations for particular, either the details of specific events or how things, the mechanisms that are responsible.
Again, I remember Steve Gould saying many times that evolution itself is as factual as the Earth going around the sun. It's the mechanisms by which evolution operate that's theoretical, and that we all debate behind the scenes.
I mean, to me, it's like denying gravity.
There you go.
Don't.
You can say it, but it's kind of compelling that it's true.
Someone here. This gentleman has a question.
You both are apparently field biologists. Can you hear me?
Yes.
A little loud, yeah.
You're both apparently field biologists. You've indicated that there are perhaps 10 times as many unidentified species as there are species that have been described. But there are a lot of people worried about extinction. Can you comment on the rates of extinction, the rapidity, and whether that's a concern to you, or should it be?
Good. That's yours.
Yes, extinction is a tremendous problem. It's something I'm particularly sensitive to because, as probably is evident by now, I specialize on amphibians. And amphibians are one of the key groups right now which are under particular threat. About a third of the world's species of amphibians are critically endangered and may go extinct in the next 20 years. This was recently an assessment made by the group Conservation International. What's particularly tragic to me is these species are going extinct. At the same time, we haven't yet finished inventorying all the ones that are out there. I literally am describing one of the impetus for describing the species that we've discovered is many of them are on the verge of extinction. So we're trying to get names on these things before they literally go extinct. So it's a severe problem. And, that's all I can say. It's a real tragedy. Yeah, absolutely.
But I've often wondered, as by the same token, how many new species, for example, in the Amazon, are emerging this very day?
There are, yes, speciation, the process of evolving new species, is continuing today. But if you look at the rate of speciation, how long it takes, usually people speak on the order of a few million years for evolution of a new species. In some extreme, exceptional cases, people have been able to claim, well, maybe 50,000 to 100,000 years. So new species are evolving, to be sure, but at a rate that is several orders of magnitude less than species are being lost.
Okay.
Yeah, Jim said that for planet Earth better than I could, but let me tell you the one species I worry about quite a bit, and that's something on Mars. And the reason I worry about that is if there is life there and we are not careful going there, we send men way too soon, or we joke, you want something with good mobility, but is disposable, so you send graduate students. But anyway, the point is that if there's something there, you want to be able to observe it. If it could be our cousin, it could be our ancestors, it may be a completely separate origin of life. But if there's something there, I sure want to know about it before we go destroy it.
But haven't we already done potentially that? We've sent several rovers there. And how well have they been sterilized?
All of them have to go through. Believe it or not, NASA has a planetary protection officer. I know it sounds like Men in Black. John Rummel. He's not a man in black. Very nice man. And he worries about these things. There are international treaties that we sign discussing how much the biological load has to be taken off. But there's no craft that we send that's absolutely sterile. But we do our best, and I'm sure we're okay at the moment. But once we start getting humans up to these places, all bets are off for field biology.
How about a question way in the back? Laura has somebody way up here in the bleachers. We can't quite see you anywhere, but speak up.
Two quick questions. One is, what is it about carbon that makes it such a special molecule? Is it just that it's lightweight and can form 4 bonds, and therefore you can have a lot of scaffolding? And the second question is...
You answer.
That's it.
Oh, all right. I've often heard it said that there's a certain chirality or handedness to all life on Earth, and could you discuss that?
Do you want me to go for that?
Yep.
Okay, there are a couple of schools of thought on that. As you alluded to, all life on Earth uses left-handed amino acids and right-handed sugars. Why, we don't know. It could just be it's been called a frozen accident, that the dominant form of life used that on Earth, and that's what we've kept using. I just reviewed a manuscript from someone who is suggesting that there are other forms of life on Earth today. We just don't bother to look for them. One other sort of intriguing, I find actually really intriguing idea is that when you form the solar system, when you form the stars in the solar system, because of the radiation coming out, there may be a chirality imparted onto the molecules as they form. And if this is true, you would expect all life then within our solar system to use the same chirality. But I don't know how firmly established, but I know that idea is out there.
That's true if the radiation from the star system is polarized. That's a leading possibility. Did you want to comment on that at all? That's okay. Let's move on to another one right here, this gentleman in the front row. Did you have one? Yeah, please.
If you move time out 1,000 years, 10,000 years, do you think we've plateaued our own species and our own intelligence? As we smart as we ever going to get? And secondly, do you think that...
I think we've already started on the downhill.
And secondly, did modern man really begin when we became bipedal?
That will be an especially good question next week when Fred Speer is here as an anthropologist from Amsterdam. But perhaps Lynn or Jim might want to say something briefly.
You're the multicellular man.
I mean, the problem with that intrudes when you talk about human evolution, I presume this is what they will discuss, is the idea of cultural evolution. Yes. It's no longer, human evolution is as much cultural now as it is biological. And so it's very difficult to assess what is intrinsic in the genome, and also natural selection as applied to humans is a very difficult thing to assess these days. And in a strict definition of evolution would insist that there be genetic change over time from ancestor to descendant. And it's not clear to me that there's that much of that taking place anymore.
This gentleman right here.
This is directed at the young lady. Thank you for an awesome...
Thank you. Thank you. Let's just stop right there.
An awesome presentation. Unbelievable. And I want to direct a question at a very specific, narrow point. That has to do with the origin of life. Is the origin of life based, at the present time, basically a speculation or hypothesis? You didn't seem to prove that it was originated back in the past, but rather the possibilities are there with atmosphere, oxygen, and all the other catalysis and so forth. And the other companion question, and I'd like you to respond to that question, the other companion question is, has science ever created life? Has science ever created life in either a plant or an animal or an insect or anything? Thank you.
I suspect Jack Shostak is not in the room because he's working on it right now. There are people working on creating life in various ways. They have recreated a virus, but that's pretty simple. You just take the sequence of nucleic acids and you join them together, and you've got your virus, basically. There are people working on it, and yet there seems to be this enormous gap between life and non-life that we haven't figured out. And like I say, it may turn out that it's in the newspapers tomorrow, and we could all go home and make our own life during the weekend. It may be incredibly simple. It may have been incredibly complex. I mean, it's a weird situation. We know all the components. We could take ourselves or bacteria or anything. You can grind it up. You know every single thing that's there. But we don't seem to be able to make it. And even if we do, that doesn't prove that that's the way it happened on Earth. So it's one of those weird things, and I like to think that we'll know within our lifetime. I think someone said in a lecture that when you get to these questions, everyone says it will happen and then they take the number of years till their retirement, and then they subtract about 5 years. So I hope it's within that time frame that we all know, but it's a very tricky question. And the funny thing is, we think about it from that angle, but it's equally relevant, this whole question of what is life, to talking about end-of-life issues, beginning of life. What's the difference between someone or a bacterium or a worm that is alive versus dead? There is something about life, and I don't want to sound like a vitalist, but there's something there that we haven't grasped. And I'm going to try to avoid going into any more detail because I've given whole lectures on that. But it's just a fascinating question.
I'm afraid we have time for only one more question. Laura, did you give the mic to someone up here? Yeah.